Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to do a practice problem using Gibbs free energy. Now, what I've done is I looked up some thermodynamic values in the appendix in my textbook. So at the end of my book, there's this appendix that has all these values for enthalpy, for entropy, and for Gibbs free energy. And I looked up those values. Now, all three of these use the same kind of equation of the sum of the products minus the sum of the reactants will give you delta H, delta S, or delta G. Okay, so what I'm going to do is I'm going to sum up my products and subtract them from the sum of the reactants, and I got this number for the delta H, the enthalpy change. I did the same thing for entropy. I summed up the products, I summed up the reactants, and I subtracted the two, okay, and I got this value for the entropy change. And then finally, I did that for delta G. I summed up the products, I summed up the reactants, I subtracted the two, and I got this number. You can do a quick check if you want to pause the video and check my numbers, okay, but they all work out. Now, what we're trying to do in this practice problem is what happens if we don't have an appendix and we don't have all those values, and instead the prompt gives you the enthalpy change, and it does give you the entropy change, and it wants you to figure out what the delta G is, okay? But they're not going to give you these values, okay? So they give you this, and they want you to get to this answer, and you have to use an equation that we're going to use in this practice problem, okay? So let me erase this and show you what that equation is going to look like, okay? So when dealing with enthalpy and entropy, a lot of times those values are used to calculate Gibbs free energy. And the equation is that delta G, or Gibbs free energy, is equal to the enthalpy term minus the entropy term, which is temperature times delta S. So this is the enthalpy term, and this is going to be our entropy term. Now, this temperature, it can't be in degrees Celsius, okay? Because degrees Celsius can be positive or negative. It has to be in the Kelvin scale, okay? Because when you're in the Kelvin scale, you can't have any negatives. There's no such thing as -1 Kelvin. Kelvin is always a positive number. So we know that this guy is going to end up being positive. So let's go ahead and just plug in our values for delta H and delta S and see if we can come up with this delta G answer. So my delta H is negative 571,000. I'm sorry, let's try that again. Our answer number is negative 571.66 kilojoules for the enthalpy term, okay? My temperature, we're going to pretend we're at room temperature, so in Kelvin, that's going to be 298 Kelvin, and that's going to be multiplied by the entropy, which is negative 326.36, and I want you to pay attention to these units. This is going to be joules per Kelvin, where the enthalpy is in kilojoules, and that's going to cause us some problems with our units that we're going to have to resolve, okay? So as you can see, when I multiply the temperature by the entropy, the Kelvin is going to cancel out, and when I multiply those two numbers together, I will get a number of negative, I get 970, I'm sorry, 97,255. 97,255 joules. Well, you can't subtract kilojoules in joules. The units have to be the same. It'd be like subtracting apples from oranges and having you that tell you something relevant, okay? It doesn't. You can't take 5 apples and subtract 2 oranges, okay? It doesn't make sense. So the units have to be the same. So what I'm going to do is I'm going to convert these kilojoules over to joules, okay? And when I do that, I got to multiply by 1,000, so I'm going to move this over 3 places. So instead of being a decimal, that's going to be a comma. So negative 571,660 minus this negative 97,255. So let's kind of put that in here. And when you get in your calculator and you subtract these two numbers, okay, you're going to end up getting negative 474,000 405 joules, okay? Of course, if I were to convert this back into kilojoules, okay, that would be equal to negative 474 kilojoules to 3 sig figs, and to 3 sig figs, we get negative 474 kilojoules. So I just wanted to show you that this reaction works. Now, some of you might be concerned about, hey, this is 405, hey, this is 0.26. It's because these values are coming from a thermodynamic value, but to 3 sig figs, they're exactly the same. So it's like, I guess, close enough for what we're doing, okay? So I just wanted to prove that this equation works, okay? And what we're going to do next is decide, hey, does this reaction work? Well, if you remember from the last video that we just did, is that if delta G is negative, and it's negative either through products minus reactants or this new equation that we're learning right now, okay? If it's negative, that means the reaction does occur, okay? So this reaction is thermodynamically favorable, it is spontaneous, or it will occur. These three things mean exactly the same thing, okay? Now, what we're going to take a look at next is this chemical reaction always going to work, okay? Remember, both of these are negative signs, okay? So if this is a negative and you subtract another negative, does that always equal a negative sign, okay? Will this always be negative, meaning the reaction will work? Not so, okay? At the lower temperatures, it will work. Like if this was 0, basically this term doesn't exist. And if enthalpy is negative, then delta G will be negative, which means the reaction will work. But if we jack up this temperature enough, okay, the entropy term will be larger in magnitude than the enthalpy term. So if we had something like negative 100 minus negative 500, okay, what does that turn out to be? Okay, well, negative 100 minus 500, when you do subtract a minus, it's like adding. This would end up being like positive 400, okay? If you get a positive sign, what that means when it comes to delta G is that that reaction will not work, okay? So what we know right now, okay, is that 25 degrees Celsius, okay, this reaction works, okay? And it looks like if we took it all the way down to 0, it would work. So this equation, it works at the lower temperatures. But there's going to be a point where if you increase the temperature enough, this reaction will no longer work. And that's our second question for today. What is that magic temperature in which this reaction works or is spontaneous, and it switches over to not working or being non-spontaneous? Okay. Well, what you do is simply by taking delta G and setting it equal to 0, okay? Because that's the point in which a negative would turn into a positive. So as you go from negative numbers to positive numbers, you got to cross 0. So we're going to set this equation equal to 0. We're going to plug this number in. Remember, we're going to put it into joules so those units match up. So this is, again, going to be equal to negative 571,660 joules. So all I did is I moved the decimal point over 3 places to convert the kilojoules into joules. I'm going to be solving for my temperature, and the delta S is equal to negative 326.36 joules per Kelvin. Okay. The first step is to move this over to the other side of the equation. So this is going to end up being a positive on the other side because I'm going to add 571,660 to both sides. So this is now a positive number. And that's going to be equal to, we got a kind of like a minus, so that makes that positive. This ends up being T to the 326.36 joules per Kelvin when I take care of the negatives. And what I'm going to do is I'm going to divide both sides by this 326.36 joules per Kelvin. The joules are going to cancel out, and I'm going to be left with a Kelvin. If you go into your calculator and you take 571,660 and you divide it by the 326.36, you get a temperature that's equal to 1,752 K. So what happens is that this reaction will work from 0 Kelvin all the way up to 1,752 Kelvin. Delta G is going to be a negative number. So in this range, the chemical reaction works, okay? When you're at 1,752 K, delta G is equal to 0, which means the reaction works in the forward direction and the reverse direction. But if I ever went above 1,752 K, delta G would be a positive number because this temperature just got too high and it made delta G positive. And if it's positive, that means the reaction will not occur. So once again, this reaction is spontaneous. It will work as long as delta G is negative, and that happens from 0 Kelvin up to 1,752. At 1,752, it works in both directions, and above 1,752, this reaction no longer works. And this happens when delta H and delta S are the same sign, okay? When they're the same sign, it's going to be temperature dependent, and you have to do this type of work to figure out what the magic temperature is and where it switches from working to not working or not working to working, depending on the signs of delta H and delta S. If you found this information useful, please give it a like and subscribe. Adding that comment will really push this information out to other students that are interested in learning chemistry.